All right, guys, welcome back. So we're gonna get started with chapter three, and this chapter is basically about having an intelligent agent, or having an agent be able to find a solution to a problem through doing searches. Right. So a good chunk of this chapter is showing you different ways that you can search across different data structures. So what's going to be confusing about this, what's going to make this chapter tough, isn't the fact that you're going to have an agent that is searching through data structures to find a solution to something. It's going to be the fact that the way you build your data structures in this chapter and in AI, I guess you could say, is different than what you did in your data structures class, right? So in your data structures class, you'd build a binary search tree or whatever, and then you'd add a bunch of code or a bunch of nodes to it, and then you'd run a search algorithm, right? You build the tree first, and then you search it. Okay, that's great. You understand how the data structure works, but it's wasteful, right? It uses a lot of resources, and depending on the situation, that's not a problem. But in AI, the a rule of thumb, I guess you could say that the less resources you use, the smarter you could become. Okay, and so what's happening with these algorithms we're going to look at is that you're going to be generating the tree as you're searching it, and so that's going to be a little weird. Okay, and so what I want to do before we dig into stuff is I want to take you to Blackboard really quick, and I want to show you the references section here, right under modules. Okay, and see there's this link here. It says implementations of all pseudocode algorithms in the textbook. Okay, so I'm going to click on that, and I'm going to take you to the site. So the textbook authors, they wrote solutions, right? They wrote code examples of this pseudocode, and it's going to be really important that you can read the pseudocode and implement it and modify it for your needs, right? For the agent that you're trying to build. And so you can see here that we've got implementations in Java. We've got implementations in Python, right? We've got the pseudocode itself. We've got implementations in Lisp. I mean, there's implementations in C#, right? So all kinds of different languages. Now, what I want to tell you is use this code at will, okay? Don't necessarily think that you have to build everything completely from scratch. Refer to this place often, okay? To get a better feel for how the pseudocode translates into actual source code, right? Or into actual computer code. So what I'm going to do is I'm going to go to this Python section here because I think Python's the easiest to read out of all of them. Well, I mean Java is too, but I'm just going to go to that. And so if you scroll down, okay, you'll be able to see that there's, it gives you a list, an index of algorithms here, right? So we're going to look at, we're going to be talking about a problem. We're going to be talking about nodes. We're going to talk about queue. We're going to talk about tree search, graph search, breadth first search, uniform cost search, depth limited search, iterative deepening search, best first search, A-star search, in just chapter 3. So you can see, these all go, these numbers here, 3.1, 3.2, 3.7, and so on. These go with the figures in this, of the source code in the text, right? So it's really important that you can understand what the source code is doing, and I'm holding your hand initially. I won't be doing that the entire course. You should be able to read it after this chapter really. But it's important that you understand what it's doing because that's a blueprint. It's telling you exactly what to code, and all you have to do is kind of modify it for your needs. But let's go take a look at. Let's go ahead and take a look at. Let's see here, tree search. Okay, so click on that. Okay, and this brings you to some code that shows you, what we're talking about. So the textbook is going to tell us about these functions, right, that we have to define for a problem. Okay, and so it gives you an example of what this looks like, right? There's going to be an actions function. There's going to be a result function. There's going to be a goal test function, a path cost function, right? So this is giving you an example of what it's talking about. Okay, we're going to talk about how we have to create a node that represents states within the search tree or within the search graph. And so here's an example of it in Python, right? So as we're building these data structures, we're going to need a node that is going to be keeping track of some key pieces of information. One key piece of information is going to be the state of the world, okay? Another is going to be keeping track of a pointer or reference to the parent node, okay? There's going to be an action that caused this state to be generated, okay? And then there's going to be a cost of all of the decisions being made to get you to this state, okay? So I just want to bring this up and remind you that this is here. That link that I put on Blackboard, it's not just there for funsies, right? You're going to be writing your code, right? I'm not going to co-author your code for you. I'm not going to help you debug it. I'm going to explain how these things work at a high level, and then I'm going to give you some assignments, and then you're going to have to, implement, some solutions or come up with some solutions. So learn it, love it, apply it to your life. Utilize this code as much as you want. It's here. Use it. Another thing that I'll point out: depth first tree search, breadth first tree search. We're going to see. I'm probably going to do this video across a couple parts because this is going to be the longest chapter that we've had so far. But you're going to see talk about the frontier. You're going to see talk about the explored queue, right? And it's literally a explored queue. It's a set here in Python, right? But in C++, it might be a vector. In C#, it might be some form of array. In Java, it might be an array list. Okay, so we're going to be talking about things in the abstract, and then it'll be up to you to just code the thing, right? Translate that pseudocode into actual computer code to solve the problem. Okay, so I just want to point out that that's there, and you're going to really want to refer to it often, okay? Because you'll be able to see the pseudocode translated into some real language. And as I was saying, there's implementations in Lisp, in C#, in Java, in Python, right? And if you only know C++, the code in Python, maybe it's the easiest to read. Well, if you're only thinking about C++, then Java, right? I mean, Java is very C++ like, but if you don't have experience with that, or you're mostly a Java programmer, well, go look at the Java code, right? Or if Python's more your thing, go look at the Python code. So there's implementations of all of that pseudocode there for you to be able to get a better feel for how it looks, right? And what the pseudocode is doing and how it translates into actual computer code, okay? So let's go ahead and get started then on the Chapter 3 content. Let me switch over here really quick. All right, so there we go. Thank you, OBS. So let me go ahead and start talking about this. So we'll go through about the first 40 or so slides, maybe 50. And like I said, we'll try to break this up into multiple pieces so it's a little bit more digestible. Okay, so Chapter 3 is all about solving problems by searching, right? So as I was saying, you're going to be making these data structures, and each node in the data structure is essentially going to represent a possible state of the world, right? A possible arrangement of chess pieces on a board, checkers on a board, a certain layout. All the different places where the NPC could be in the world, okay? And there's going to be actions that can take that can modify the state of the world that could happen, okay? And a solution to the problem is basically going to be a chain or a list of all those actions that take you from your initial state of the world when the game starts to a goal state, okay, in the world. That is where you want to be. And so each node represents an intermediate state from start to finish, and each edge that is connecting those nodes represents an action, Okay, and so you'll come up with some kind of encoding scheme for representing a state in whatever it is that you're trying to do, and some kind of encoding scheme for representing actions, right? So that's one of the reasons why the textbook provides pseudocode and also leaves a lot of that code like undefined in that repository that I showed you, is because what you write is going to depend on what type of agent or what you're trying to do. Okay, so there isn't just some blueprint. There isn't just some well, I mean, it's a blueprint, but there isn't just some like cookie cutter, copy this code and it just works kind of thing. You got to tailor it, understanding using what you understand about the principles of AI. Certainly when you're, at least in this chapter, when you're solving problems by doing searches on data structures. Okay, so here's the topics we're going to cover. I think we can get through these first 3 sections in this video, and then we'll come back and we'll hit 3, 4. We might have to do 3, 4 all on its own, and then come back and finish with 3, 5, 3, 6, 3, 7. Because 3, 4 is going to have a lot of different data structures in it, and talk about different ways you can search through them. But we'll see. I mean, the first couple of them I'll go through in pretty good detail, and then after that I should have primed you for digging in a little bit more on your own towards the end. So maybe I won't beat a dead horse there, but we'll see how it goes. We'll see how it goes. Okay, so reflex agents, simple reflex agents, like we talked about in the previous chapter, they're limited, right? So reflex agents were agents where percept, action, percept, action, percept, action, percept, action, right? They just simply respond by instinct to something that they perceive. Okay. Now, agents that are goal-based, they're much more capable. Okay, they can be more sophisticated, and they're capable of more sophisticated decisions. Okay, or making more complicated decisions anyway. So one type of goal-based agent is known as a problem-solving agent, and so that's what we're going to talk about right here in this chapter: a problem-solving agent. So problem might be how to win the checker game, or the problem might be how to get that floor clean, or a problem might be how do I arrange all these pieces on a chessboard. And that's what we're going to look at. We're going to examine some of that as toy problems, just so in the abstract at a high level you can understand the elements that go into a problem-solving agent, where you're using data structures, searching through data structures to find your solutions. Okay, so these type of agents, remember we talked about the 3 different representations of the state of the world or the environment? Well, these guys are using atomic representations, right? That means that each one of those representations of the world is indivisible, they're discrete, right? You shift from one state of the world to another, and they're very, very simple, relatively speaking. Right? Whereas, with the other types of representations, factored or structured, factored was able to keep track of a whole bunch of different variables, combinations of variables, lists, and all that kind of stuff. Structured was dealing with, relationships and whatnot. The problem-solving agents, they're going with the atomic representations, right? Very, very simple. Yeah, we're starting off, right? We're starting off chapter 3. We're still early in this discussion, right? But when you have agents that are factored or structured, those are often called planning agents. Okay. Now, in order for us to build a problem-solving agent that is using these atomic representations, here's what we need to do. Okay, we have to come up with a problem, okay, that it's trying to solve. And you need to come up with definitions to help you describe that problem. Okay, and problem-solving agents search for solutions that solve the problem that you defined. Okay, now the way you find those solutions is by using a search algorithm. Okay, so it's like with everything else in computer science, you're always coming back to algorithms, right? It's about the algorithms. It's not about, there's 4 bytes of an integer, or you can only have so many items in this list or whatever, hash tables or more. It's about algorithms. All right, so we got 2 types of search algorithms that we're going to look at in this chapter. The first is going to be uninformed search algorithms, and the second type is informed. Okay, so with an uninformed search algorithm, there is no external guidance. Okay, it's kind of a brute force algorithm where it's just going to try a whole bunch of stuff until it finds what you need. Whereas with informed search algorithms, we'll utilize or we'll talk about how you can utilize these things called heuristics or heuristic functions, which can utilize information that's outside of the problem definition itself to help guide the search a little bit. Not a ton, but a little bit, right? And it's going to be simple. In the next chapter, we'll be able to turn this up another notch. All right, so problem-solving agents, section 3.1. Goal-based agents. It's in the name, goal-based. Have to have some kind of goal, something that you're aiming for, right? Something where you're trying to get to. Okay, so the first step to solving the problem is figuring out, well, what's the goal, right? Where am I trying to go? What am I trying to do here? Okay, what's the agent? What state of the world am I trying to get to with this agent? Okay, so a goal, you can say, is a set of states. Okay, now what's a state? A state is a single representation of the world. So here we're talking about atomic representations. Okay, and we'll dig into this, and I'll give you a couple examples here in a second, right? But for right now, just say a goal is a set of states. Okay, now problem formulation, that's trying to figure out all of the actions that an agent has to take and all of the states it has to transition through to get to that given goal. Okay, so you start off with one particular arrangement of the checkerboard. Okay, and if a goal is that there's only red checkers left on the board, right? There's going to be a series of actions which take you through a series of states that eventually end up where the state of the world is in a situation where there's only red checkers on the board, right? So in this context, what's an action? Moving a checker from this square to that square, right? And when you do that, when you move a checker from one square to another, you transition from one state to another, okay? So a current state plus an action gives you an updated state, all right? So you got to know the actions and states that it takes to get to a given goal. And if you lack any other information, right? If it's not a state where everything's known, for example, then you can say that the environment is unknown. Okay, so example, you got a self-driving car, has a map, right? Well, that's a known environment. Okay, so all of the actions it can take, all of the different places the self-driving car could be at a particular instance of time, think city, that's a known situation. But if the self-driving car doesn't have a map, well, then it's an unknown environment. If you have the map, okay, if the agent has the map, it is now capable of deciding what to do. Okay, so it can think ahead in its mind. It can say, well, I need to get from San Francisco to LA. So I got a map. I know about the environment. Okay, one action could be drive from San Francisco to Oakland. Another action could be drive from Oakland to Hayward. Another action could be drive from Hayward to Fremont, and so on. Right? You can think ahead. You can plan ahead. It's a planning agent. Okay, until eventually, if your goal is car in LA, eventually, as you're thinking ahead, as you're planning out your actions, the car eventually ends up in LA, and that's, you've hit your goal state, and now you have a plan, you have a series of actions that solve your problem. What was the problem you're trying to solve? Get the self-driving car from San Francisco to LA, okay? So, remember we were talking about task environment, previous chapter. If an environment is observable, discrete, known, and deterministic, the solution to any problem within that environment will be a fixed sequence of actions, which I just said, a fixed sequence of actions. So the environment has to adhere to these 4 attributes for this to work. Okay, the solution is just going to be action A, action B, action C, action D, action E. Each one of those actions modifies the environment to a certain extent, which leads to the next action. Okay. So plotting a course from one city to another. This is what I was just talking about, the self-driving car going from San Francisco to LA. Okay. Now, to figure out what those actions are, right, to get us from our start state, our initial state. The initial state is car in San Francisco. To get to the goal state, what's the goal state? Car in LA. Okay, what we have to do is we have to do a search. Okay, so you've got a problem that you've defined, and there's characteristics of that. What are the possible actions I can take? What are the possible states that can happen? What's it cost to take an action? Okay, you define that. What's the environment? You define that. What's the result of me taking an action? Then you apply a search algorithm to that problem, and then that leads you, or that gives way to your solution. Okay, so that search algorithm is given a problem, and if you look in that source code that I show you at the very beginning, you're going to see what I'm talking about. What they're doing is problems are defined as classes, and they're extending that class into a search algorithm essentially. Okay, now you don't necessarily have to write the code the way they do. I'll give you guidance on that, but I'll be looking for these elements that we're going to be discussing in your code and when I determine your grade. Okay. So search algorithm has a problem that it operates on, and it returns a solution. What's the solution? A sequence of actions. A sequence of actions. So how do you define an action in your computer code? Pick whatever you want. You're like, what the hell are you talking about? Pick what I want. What are you fun? You're not helping me. An action could be turn left. Okay, so you have to represent that somehow in your program. Maybe it is octal 7. Maybe it's the string literal left. Maybe it's a bit that's flipped to 1 in a short integer. You see what I'm saying? You can make it whatever you want. You just have to be able to represent that action and then be able to represent a state in memory in some way, right? It's up to you when you're designing this to pick, okay? All right, so once you've got that solution, that sequence of actions, and by the way, that sequence of actions, how about a C++ vector with a bunch of integers, where each integer represents a potential action, okay? How about a Python list with a bunch of strings in it, okay? Where each one of those strings represents some kind of action. How about a Java array list that's stuffed with a bunch of objects, where each object represents a type of action? The possibilities are endless. What's important here is that sequence of actions makes up the solution that your code or your program can then pull apart and then apply those actions to modify the environment as needed. So the execution phase happens after the search phase. Okay, so that's when the solution is put into action. Now, once the execution phase is complete, then the agent needs to figure out, well, what's my next goal? What am I trying to do next? Okay, so the agent, while it's in its execution phase, while it's thinking, it's ignoring percepts. Why? Because it already knows what it's going to do. When it's executing the solution, it's locked in. Okay, it's automatic, right? It's figured out what it needs to do, and now it's going to do it. So this is kind of dangerous for a self-driving car, right? Because a self-driving car might say, okay, my action is to drive from San Francisco to Oakland, and then from Oakland to Hayward, and then it just stops thinking, just starts driving, right? Somebody comes along and pulls out in front of them, you just run them down and keep on going, right? There's no new percepts. You're executing the action. So this is kind of limited, right? It is kind of limited. Okay, but it does have its uses, and this is kind of like the simplest example I'm going to start with. So your eyes are closed, right? So this is what's known as an open loop system. Okay. Okay, so let's talk about well-defined problems and solutions. So a problem, right? You'll see in the source code, they have implementations of this. A problem can be defined formally. 5 pieces of your problem. 5 pieces of your problem. And we'll pull this apart, okay? We'll break this down. So an agent is going to find itself in an initial state, okay? In an initial state. And so you have to define, well, what's the initial state? Where's the agent starting from? Okay, and then you have to describe within what we're calling this problem. What are all the possible things that the agent can do? Right? And then you have to have a transition model. Right? What state do you end up in if you take an existing state and then apply an action to it? Right? The state of the environment that the agent finds itself in, it takes an action. The transition model says, okay, well, this is how, or this is what the new state of the environment is going to be. A goal test. Am I in the state that I was trying to find? Right? Am I in the state of the environment that I want to be in? If so, then I've passed I've gotten my goal. I've attained my goal. And then there's a path cost function. And a path cost function is a way to evaluate a particular one solution against another. Okay, it's a way to provide a metric for measuring, whether one solution is more efficient than another. Okay, there's other ways too, which we'll talk about. Okay, so let's talk a little bit more about initial state and give you an example. So, the state the agent starts in. Okay, the state the agent starts in. So, a checkerboard. Okay, all of you have an agent that's playing for their team red. They're the red team. They're the red player. Okay, so the agent, when the game starts, is gonna be in such a state that all of the red checkers are in their starting positions, all of the black checkers are in their starting positions, or tic-tac-toe. Right? Maybe the agent goes first. What's the state that the agent's in? Empty board. It's its turn. Right? Here's another example using first-order logic notation. Okay, a car, self-driving car. It's in the garage. Where is it in? It's in the garage. Okay. Now, what about actions? Well, actions define what the agent is capable of doing. Okay, so here's a definition from the text. I mean, each possible action is applicable for a state S if an action S function lists them in a sequence of states. Okay, what does this mean? Well, you're going to have an actual entity in your code called an action function, right? And so if you have some state that your agent finds itself in, the tic-tac-toe board, right? The tic-tac-toe board would be state S. Okay. Now, however you want to represent that, maybe it's a 9-element array, maybe it's a 2-dimensional array, whatever. You pass that as an argument to some function, okay, to some subroutine, to some subprogram, and then that function, that subprogram, that subroutine generates a list. Right, a list of states, a sequence of states, okay, that could be the result. Or here's, for example, right, the action, you're in garage, right? So you're in your garage, okay? And that would be state S. So you pass it to this action function. And so that action function tells you or gives you a list of everything that would be possible for you to do from state S. So leave the garage, go to the street, turn right. I feed the blank tic-tac-toe board to the action function. What does it give me? A list of all of the places where I could put my X, right? If X goes first, upper left hand quarter, X upper left, X upper middle, X upper right, X middle left, and so on, right? So the action function takes as an argument a state, and what comes out is a sequence of actions that can happen or that I can take that are legal. Okay. I'm looking at the way I wrote this right here, and I might need to revise that because that's not very clear, is it? Each possible action is applicable for a state S if an action S function lists them in a sequence of states. If an action function lists them in a sequence of states. Well, yeah, I mean the state here would be garage, would be street, would be right. So, forget my musings here. Let me just remind you. State goes into an action function. Action function produces a list of everything that the agent can do from that state of the environment. So it's just what the agent can possibly do. Okay, this is I gotta clean this language up right here. This is gross. So I apologize for that. All right, so the transition model, that's a description of each action. Okay, so you got some function called result, right? So you take some state S again. Okay, so for example, you got that tic-tac-toe board, okay, and you pass that into this function, and then you also take one of those actions that was provided by the action function, okay, and X upper left, right? That was the action, and you might define that action. You might represent that in your code in many different ways. It could just be action A, action B, action C. You could come up with integers, action 1, right? You could have an 8-bit integer, right? You could use or just a byte, right? And then the first bit or the high bit represents the upper left hand corner of the tic-tac-toe board, whatever. Okay, whatever you're using to represent your state and your action gets sent into the result. Okay, and so what the result does is then generates the possible updated state. Okay, and that's going to give you the state when some action A is performed on a state or in a state S. So a state plus an action results in an updated state. Okay. All right. So what's the successor? Any state reachable from any given state through one action. Okay. So that successor state, for the case of the tic-tac-toe board, was me putting the X in the upper left-hand corner. That would have been one action. The blank tic-tac-toe board. What's the successor state? It's tic-tac-toe with an X in the upper left-hand corner. Okay. Or in the example of the car in the garage, right? What was the first, or what was our initial state? What was the state? We were in the garage. So we applied an action. What action? Go to the street. Okay, so what does that result in? Our successor state. What's the successor state? The car's in the street. Where did this go street action come from? Came from the result function. Okay, or excuse me, from the actions function. Sorry, from the actions function. So in garage goes into the action function. What comes out of the action function? Well, one of them is go street. Okay, and so then you want to see, well, what's the result of that action? Feed go street, and I'm in the garage. And then, my new state, my successor state, is in street. Okay, so you can code that in many different ways. I mean, you need to have a decision structure in that result function. You can just have a bunch of if-else statements, right? I mean, you can do it in all kinds of different ways. So the initial state, all of the actions that are possible in that transition model, that's going to define what's called the state space. Okay, the state space, right? Now, that state space provides us a graph. We're going to have a graph, okay? A graph of states, in data structure terminology, nodes, right? Or in graph terminology, nodes. And each one of those states is connected by some kind of an action, right? So the edges in the graph represent actions. Now, if we were talking about in a data structure like a binary tree or just a tree, the edges, the actions, would be pointers, okay? And each node is representing a state. So a path in that space is a sequence of states connected by a sequence of actions. So when you have a path going through that state space, right, you're starting at your initial node. That's your initial state, okay? A node contains a representation of a state, okay? You got a pointer, you got a pointer, you got a pointer. Each one of those pointers, you've got 3 other nodes. Each one of those nodes contains a successor state, okay? And so connect a bunch of nodes together. They're connected together by what? These actions, right? And all of those in sequence give you a path, okay? Now the pointers are a concrete representation, but we're gonna have this abstract idea, the fact that an action is tied to this edge, which is in the concrete, a pointer or a reference. So you have a goal test function. It's just figuring out if a particular state of the environment is a goal state. What's a goal state? That solves your problem, right? Having the agent in that state or in that state of the environment is solving your problem. That's your goal. Okay, so for example, you want that self-driving car at the store. Okay, then a goal state is at store. Or in the self-driving car example, at LA, in LA. Or my checkers example, all red checkers. Okay, but you can have a set of goal states too, right? You can have a set of goal states. So there's more than one way to win tic-tac-toe, right? If I'm going first, if I'm the X player, if my agent is going first, it's the X player, then there's multiple goal states that work. As long as it's 3 in a row, top row, middle row, bottom row, left column, middle column, right column, diagonal, right? Those are all goal states. And if you can find a path through all of the nodes that get generated representing different states, from blank board to 3 in a row of some kind, you've got a solution. Because each edge through that structure is going to represent an action that you take. X here, O there, X here, X here, X here. Well, I say O, but we're not talking about adversarial searches yet. That's in chapter 5. But you get the idea, right? You make a move, and then blank board, take an action. Another node gets formed with X in the upper left, where it represents a state with X in the upper left-hand corner. Now from there, what's the next action that X could take? Well, maybe it puts the X in one square over. That generates another state, right? And so on, until eventually, hopefully, you got 3 X's in a row. So going from blank to 3 X's in a row, that's your solution, right? And then each connection between those represents an action. Okay. Path cost function. You're just trying to come up with a cost, right? So you're coming up with some kind of score for each path. Right? And since a path is a sequence of actions that leads to a goal, if one path is shorter than the other, it would mean in the tic-tac-toe example that you won in fewer moves, right? So a lower score there might be better, So you're going to have a desirable cost function that's going to allow you to figure out, scores, right? In a way that allows you to decide amongst possible solutions. Okay. All right. So here's how we can denote the step cost. So going from the current state to our new state, taking a particular action is going to generate a particular cost. That's all. Okay. All right. So let's talk about formulating problems. Right. So we're going to be working with in the abstract, right? When you're describing your problems and how you're going to be solving this thing, you have to think about this in the abstract. We're not starting our discussion or thinking about this in terms of code, int x, double d, float f. That's not where you start. You start at a high level thinking about, okay, what am I representing here? What am I doing? Right? You're thinking of an abstraction of the idea. In garage. There's no code there. Okay, it's just an abstract representation of a particular state of the environment. Blank board. Okay. So the descriptions of the different states and of the actions need to be abstracted. Right? You have to come up with some way to think about, or describe what the action is, what the state is. Okay, and your abstraction, your descriptions are good. Okay, if you can come up with a solution that can be manifest into some more detailed environment or some more detailed world, right? So in garage, well, yeah, I mean, you can say, yeah, the car's in the garage. See what I'm saying? Right. This abstraction is saying, oh, there's a car in the garage. Well, yeah, you can easily translate that into reality. You just put the freaking car in the garage, right? Or X in upper left hand corner. Well, how can that translate? Get a two-dimensional array, assign character X to, cell 00. Okay. All right. Good abstractions remove as much detail as possible while still staying valid and useful. You need to have this. You need to have these abstractions, okay, to form the basis of what you're going to code, right? And so intelligent agents, to be able to create one, to be able to craft one, to have it actually do stuff, like I said, in a detailed environment, in the real world, you have to be able to think in abstract terms and come up with representations for it. Okay, so example, want to plot a trip between cities for that car that drives on its own. Want an agent that's going to play checkers and win. Okay, and you have to have some kind of abstract. You have to think about the board, right? And you have the board, and then in the concrete, in the real world, you would have that board on the table, right? And so you can say in your abstraction, well, there's a piece in a certain square. Well, then there's a piece in a certain square in the real world. Okay. All right, so let's dig into example problems here. Give you another idea, or give you a better idea of what we're talking about, or further idea. So, textbook introduces this idea of toy problems, okay? And the usefulness of a toy problem is to be able to use them as a device for explaining much more complicated ideas, right? They're useful for explanation. So, we're going to come up with these simple examples that really are stupid. They're pointless, other than to provide a vehicle for explaining how this works. Okay. Now, real world problems, they've got solutions that actually matter, right? That actually translate into reality in some way. So this is just examples for the sake of argument that allows us to explain how the stuff works. In the real world, you want to be able to drive that car for real. Okay, so here's toy problem number 1. Okay, vacuum world. And in vacuum world, remember how we defined that. Okay, we had the agent representing a vacuum. The environment had 2 squares. Each square could be dirty or clean. And the vacuum is going to start in some initial state, right? In some initial state. So what are the possible initial states? Well, vacuum in the left space, both squares clean. Vacuum in the right space, both squares dirty. Right? So one of these states would be the initial state the agent finds itself in. Now, what are legal actions that the agent could take? Right? Well, if this is the state that it's in, right? What could you do? Remember, you could move left, you could move right, you could suck, right? So some representation of this state that you came up with in your code could be fed to an action function that you write. And so what comes out? Some representation of left, right, suck. Okay? And so then for the results function, you feed in this state, you feed in the left action, and so what comes out of the result function? This state right here. Okay? Similarly for suck and for right. Okay? So these 3 states, right, are subsequent states to this guy right here. All right? All right, so to formulate it as a problem, we need to describe states. We need to describe possible states. Okay, so in this toy problem, what we have is, 2 possible agent locations, as I was just saying, and we got 2 possible dirt locations, and we got 2 different dirt states, right? 2 spaces, 2 locations, possible locations for the vacuum, and then, there's either dirt in here or there's not. There's either dirt here or there's not. So that gives you a total of 8 possible world states. Now, which initial state? We'll pick anyone. Pick anyone, right? Just make something up. And then the agent has to figure out, what series of actions it has to go through to hit its goal state. Okay, so the actions were left, right, and sub. We already talked about that. The transition model is taking some state and then applying some action and then telling you, well, what is the possible new state or updated state, right? Or successor state, subsequent state. Okay, when you've taken a state and then applying an action to it. Goal test. Well, the goal test here could be, well, we want all the squares clean, right? Well, squares should be clean. So let's take a look at the set of goal states that are possible for this problem. We got 2 of them, right? Either one of these is going to work, right? Either both squares are clean in the environments or the vacuums in the left space, or both squares are clean in the environment, or excuse me, in the vacuums in the right space. I don't know why I keep saying environment. Okay, those are our goal states. Path cost. Well, each step costs 1. However you decide you want to gauge your, the performance of your agent, the rationality of your agent, you come up with how you're going to score it. So if we assume a path cost of 1, where each action or each step costs 1, then the more actions that the vacuum takes, right, the more expensive it is. And so what we're trying to do is we're trying to come up with a path through all of these nodes, through all these states, with the lowest score possible. That would mean that you clean the floor with the least amount of effort by the vacuum cleaner, right? Higher scores mean that, maybe it kept going, it kept in a loop, trying to move right a whole bunch of times, right, when it didn't need to, for example, or kept bouncing back and forth between squares when it didn't need to, right? Those paths would be more expensive. All right, so we've got discrete locations, discrete dirt, reliable cleaning, and we're also going to have a situation where we assume for this problem that the squares never get dirty in the middle, in the midst of the agent doing its work. Okay, so here's another example, the 8 puzzle. Okay, and this is the resulting state space of all the possible states that could happen. Okay, I'm going to switch over here and give you an example of drawing out a state space for a 4 puzzle here in a second, and that's going to be your next miscellaneous assignment. But anyway, so the 8 puzzle is one of those puzzles. I don't know if you've ever seen them. Maybe bought them at like the convenience store or toy store or something like that. But they got tiles. There's a little plastic thing. They got tiles that are numbered, and then there's all the tiles occupy all the squares except for 1, and so you can move the tiles into that empty space. And so all you can do is manipulate that. Move a tile into an empty space, move a tile into the new empty space that was created from moving the first tile into an empty space. Anyway, so you can move around all the different tiles until eventually you get them in order, right? So what's the start space or the start state for an 8 puzzle? Well, you're going to have some random orientation or organization of the numbered tiles within the puzzle. Right, now, what's your goal state? Well, the goal state is, hey, I want to have them all in order with the upper left-hand square empty. Okay, fine. So we have to have, as all the possible states, what are possible states we can have? Well, the state that we can have is just some description of, or just some arrangement of these different numbered tiles within within their squares, right? That's a potential state. What's the initial state? Well, any arrangement could be the initial, or it could be the start state. When I say initial state, start state, those terms are synonymous. Actions. What are the possible actions you can take here? Well, you can take a square and move it into an empty space, right? And depending on where that empty space is, each square can move up, down, left. If it's 5, for example, it could move to the right or up, down if the empty square was here, and so forth, right? So the possible legal actions are any move that could move a square into an empty space, right? So in this case, from this start state, what are the legal actions? 2 down, 5 right, 6 left, 3 up, right? in this state, right? Let's say it wasn't in the goal state, but let's say that this was a state and we wanted to continue moving squares around. What are the legal actions? 1 left, 3 up, right? So if I fed the start state into my actions function, my actions function would return a list of possible actions: 2 down, 5 left, or 5 right, 6 left, 3 up. Okay. Now if I fed to my results function the start state and the action 2 down, right? What would it spit out? It would spit out a new state where the 2 is in the middle and then the blank space is at the top. That would be one possible result. That would be one possible successor function, or a successor state. Okay. Goal test. Check to see if it matches the goal state. Right, there's your goal state. Path cost. Each step costs 1. So every time you move a square, we'll add +1 to the score. So you want to be able to get from the start state to the goal state. The solutions that are the best are the ones where the series of actions has the lowest overall score. Okay. All right, so an 8 puzzle is what's known as a sliding block puzzle, or an example of a sliding block puzzle. And they are NP complete, right? For those of you taking your analysis of algorithms class, cool. If you haven't taken that yet, don't worry about it. It's just kind of an FYI thing. All right, so what I want to do now is I want to give you an example of all of these ideas. Based off of a 4 puzzle, okay? So let me get my Microsoft whiteboard working here, and then I'll switch over to that. So I'm going to pause real quick and I'll be right back. All right, so let's say that we've got ourselves a 4 puzzle, right? So my start state is maybe 3, 1, 2, right, with the blank in the bottom right hand corner. So that would be my start state, or my initial state, right? Sorry, I used to have a pen for this thing, but apparently that's just freaking disappeared on me. So so that'd be my start state, okay? And my goal state would be, to have it like this, right? I'm doing a 4 puzzle because I'll just label this as a G. So that way it won't take quite as long, right? So if I have this start state, okay, what are my possible actions, right? Well, the possible actions for this would be 1 down and 2 right. So if I was to feed that state into my my actions function, well then what I'd have is, what it would return would be 1 down and 2 right, okay? So then if I wanted to know what the possible subsequent states are, or successor states, I keep saying subsequent, right? These are the possible actions, okay? And the possible successor states would be the result of 1 down, which would put a 1 there, right? 3 stays in the same place, and then 2 stays in the same place. That's one particular successor state. The other particular successor state would be 2 right, okay, and 1's in the same place, and then 3's in the same place. Right, so now I got this graph building up here, okay. Now you continue on, right, building up this tree, this graph. Now from this guy right here, right, what are the possible actions? Well, I could have 3 right or 1 up, right? So I could say, well, 3 right, that's one action, or 1 up, that's another action, right? Well, what's the successor state if I was to apply the 3 right action? Well, I'd have 3 over here, I'd have 1 here, I'd have 2 here, right? What would be the successor state if I applied the one up action. Well, I just undid, potentially, got me back to my initial state here. So this is kind of a loop that's forming. Okay, and we're going to find that our search algorithm we're going to have to deal with that in a search algorithm. Okay, but anyway, I won't continue off of this subtree because, this branch, because it's just a loop. Okay, now, what about this guy over here? Right, well, what were its possible actions? Okay, 2 left. Okay, which would have a similar situation where we just undid what we did before. So that'd be 2 there, and then 3 there, and then 1. Right, so that's back into a loop there. That got us back to our initial state. So I won't continue down that subtree anymore. Okay, now over here, I could say, well, 3 down. Right, so the possible actions of this state would be 3 down or 2 left. Okay, now if I get 3 down, then that successor state is right there. Right. Now, if we continue on, what's the possible actions from this state? Well, 2 up or 3 left, right? So 2 up would put the 2 here, put the 3 here, put the 1 here. And then for this guy, it's the 3 there, and the 2 there, and the 1 there. Okay, what are the possible successor states for this? Well, 1 down would give me this, 1, 3, 2. And what about this? 2 right would be another action I could take. Okay. And so that would put a 2 there, and then there would be a 1 there, and there would be a 3 there. Okay. So you see, this is we're building our state space is what we're doing, right? And so as we're going through and building this, we're trying to find that goal state. Okay. So what about this guy over here? Well, what are the possible actions? We can get 1 left. That would be 1 action. See how it corresponds to an edge here? Okay. And then each one of these boards, each one of these configurations of the 4 puzzle, or the 3 puzzle, I guess, represents a state. Right? And they're a node in the graph. So 1 left would put me 1 there, 3 there, 2 there. And then what's the other possibility here? 3 up, right? Which is basically just the reverse of what we had. So 3 up would be 3, 1, 2. So you could potentially have a loop there, right? So we could ignore that. Let's go here and see what we got. What are the possible actions we could take? 2 to the right, right? Which would be 1, 2, 3, which leaves me to another loop situation, or 1 down. Okay. See how this tree is growing? This graph is growing. 1, 2. Okay, now over here, what are the possible actions? 2 down or 1 left. Right, so 2 down. Put 2 there, 3 there, 1 there, 1 left. Would leave me in a state like that. What about this guy right here? 1 up. This would give me 1 up, 3 right. I mean, and so on, right? I mean, I keep building this thing out until eventually I end up with a state that looks like that, right? And once I found it, that's my goal state. So let's say that it did end up being a leaf down this subtree, right? Well, what is my solution then? Well, my solution is a path, that leads through all of these states, right? And so the solution takes the form of a sequence of actions. Well, what was the first action? Well, this would have been 2 right, right? So 2 right. And then 3 down, right? And then this is 1 left. Okay, and then all these filler actions until eventually, you know, the last action that took place got me into this goal state. Okay, and then if we count each action as 1 point, then that's 1 point for that, 1 point for that, 1 point for that. So you can say that the total cost for that solution is 3, plus whatever other intermediate actions there were. Right? So by going through and generating all of those possible successor states, you end up with a graph here. And so depending on the order in which you expand or generate these successor states is going to basically determine the type of search algorithm that you're using. Okay? And so, how could you represent this in code, right? Well, you just have to come up with some kind of encryption scheme. So you might say, well, I've got B for blank and then 1, 2, 3, and that represents one state. And so this is position 0 in a list in Python, position 1, position 2, position 3, right? And so then each one of those positions, this is where the abstraction comes in, right? This is position 0 on the board, position 1 on the board, position 2 on the board, position 3 on the board. Okay, or if it's a C++ one-dimensional array that you're using, then the character B is in index 0, character 1, character 2, character 3. Okay, and so that right there represents your goal state. Okay, so if the array has its values arranged like that, then that would correspond to the blank being here, the 1 being there, the 2 being there, and the 3 being there. Now, if my initial state, was, here's the abstraction again, the blank here, and then the 2 here, and then the 1 here, and then the 3 here, well then, in my C++ array, then that would mean I got character 2 in that first element, character 1 in that next element, character 3 in that element, and character B in that element there, right? So, or maybe you use a two-dimensional array, or you use a single byte, and each bit position, right? Each bit corresponds, or pair of bits corresponds to one of these spaces. I mean, you just come up with whatever it is. You could use a character variable for this, and so if both of these are 0, then that's your blank, right? If both of these are 1, then there's your 3. 0, 1 is your 1, and then 1, 0 is your 2, right? So I mean, you just come up with whatever implementation that whatever scheme you want to represent this, as long as it makes sense, as long as it works. Okay. All right, so let's switch back to slides. But for the miscellaneous homework assignment, what you're basically going to do is you're going to generate a state space for me and tell me what kind of actions you can take and all that kind of stuff, what the goal state is, what the initial state is. And then you'll do something like this. Okay. All right, so let's continue on here. The 8 queens problem is another example toy problem here, and what you have is this is one particular state, right? And each one of these columns, okay, has at most 1 queen in it, okay? And the goal state is to have the queens arranged in such a way that no queen threatens another, right? So no queen can take another. So this right here is not a goal state because these 2 queens can't attack each other, right? And so, one action could be, move this queen to row 2, right? And so then the successor state would be the board with the queen in that position, okay? And so you just continue generating successor states until you come up with a state where all the queens are attacking each other, okay? And so this toy problem is useful for doing what? For testing search algorithms, which we're going to study in the next video. All right. So there's a couple different types of formulations here. So one example is an incremental formulation, or one type is incremental and another is complete state. And in either one of these formulations of the problem, the path isn't really considered, right? Because the goal here is just to find the final state. It's not, you're not concerned so much with the series of actions that got you there. You're just trying to figure out, all right, what's the final state, right? Is it possible? What are the actions that my agent has to take to get there? But can you just find a solution to the problem? What's the problem? The problem is that I need to get all the queens on the board so that they don't attack each other. So the path cost doesn't matter, right? You don't care about the cost of each one of those individual actions. It's just we want the final state, right? So the individual actions from state to state, that their cost doesn't matter. Okay, is the idea there. And so, for the for your first major programming project, you're gonna not have to worry about the cost of the solution either. But anyway, so here's your first formulation, your incremental formulation. So the different states, or what's a state? It's an arrangement of 0 to 8 queens on the board. Okay. The initial state has no queens on the board, and so what you're doing is you're adding. I forgot to mention this too earlier. Is that you're adding queens to different, column by column. Okay, until you have a arrangement of queens so they can't take each other. What are the actions? You can add a queen to an empty square, transition model. You're returning an updated board with a queen added to the square. And so your goal test. You got 8 queens on the board, none are attacked. So you start off with an empty board in that case, according to that formulation. Then you add a queen there, that's one action. Add a queen to another column, that's another action. Add another queen to another column, that's another action. And as a matter of fact, it's not even limited under this formulation to by column. Okay, so you can start off. Your first state would have a queen here, and then your successor state could have a queen right there, and then a successor state could have a queen right there, and then a successor state would have a queen right there. It's a lot of lack of efficiency there, because if you were to put a queen in a successor state right next to it, well, automatically that's not going to be your goal state, right? So that's kind of a waste, right? It would be better than to go column by column, because you could eliminate a lot of states that you're not interested in just by putting that additional rule in, right? That you have to go column by column. It's more efficient that way, because if you go column by column, instead of a legal action being, you have a queen here and then your subsequent state ends up with a queen right below it. If it's a column, well, then you've already eliminated how many potential successor states you have to examine, right? You're never going to generate a state where you got a queen here, 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 a queen here. That's 7 states that you don't have to create, or you have to worry about, that you have to add to your search space, right? So that's more efficient. If you only do them column by column, then there's a huge boost of efficiency. But anyway, so let's say that you can, though, right, add a queen to any square. Well, this is how many sequences that you have to evaluate. This is how many nodes in your graph you'd have to have. 64 times 63 times 62 times 61 times, all the way up through 57, or all the way down to 57. Because, when the board's empty, there's 64 squares to choose from. But once you put a queen on the board, well, then there's 63 left to choose from. And then when you put in a queen on the board, there's another queen, and there's 62, etc. So, do the math. Multiply 64 times 63 times 62. So that's a ton of sequences, which means that's a ton of nodes, which means that's a ton of states that you generated, which means that's a ton of stuff you have to search through. It's slow. But that's an example of an incremental formulation. Okay, so an improved formulation would be that one where you can only say 1 per column. Okay, and then you go from the leftmost to the right. So you can add a queen to the leftmost column, so that way it's not attack or attacked. Okay, and then you move on and add a queen to this column to where it's not attacked by the first queen. And then you add a queen to this third column, so it's not attacked by either of the previous 2, and so on until you have a queen in each one of the columns. Okay, so if you do that, you just limited the number of actions, or the type of actions that you could take. So that cuts down on the number of sequences, if you were to do math on that, from 64 times 63 times blah, blah, blah. That's 1.8 times 10 to the 14th power number of sequences. So that's a really big number. That's That's 1 and an 8 with 13 zeros after it, all the sequences you'd have to search through. But if you put this rule here, you just control the possible actions. Now there's only 2057. So you're going from bazillions upon bazillions upon bazillions of sequences to just 2,000. What do you think is going to be faster to run a search algorithm on? Right, so how you formulate the problem, the possible actions, and how your transition model works can have a profound impact on performance. Okay, and the faster something performs, and the less resources it takes, the more intelligent. You can think of it as being the more intelligent. All right. So real world problems, route finding problems are really, really, really common. You've got, you got to fly from California to Costa Rica, right? And you got to go through so many airports. Well, those type of problems, you've got locations and you got transitions. You got SFO, you've got San Jose International Airport down in Costa Rica, and you got an airport in Houston, right? And so those locations are the nodes, and those transitions are the edges. Flying from SFO to Houston, for example, right? That's a state change, and you've taken an action. Fly from SFO to Houston, right? And once that action's been completed, you're in Houston. Okay, so websites do this, use this, vehicle navigation systems, all kinds of examples of this, of where you'd have an agent that's trying to find a solution of routing stuff through different locations, military applications, airline travel, packet routing, et cetera, et cetera, et cetera. So how about a travel planning website? Okay, let's talk about a problem formulation for that. What are your states? It's like I was just saying, you've got an airport and the time, right? So airport, and you're in that airport at a certain time. Okay, you might have additional information that needs to play into this problem too, such as how long it takes to travel from one airport to another, how much it costs. Well, your initial state's going to be specified by the user doing the lookup, right? Trying to find their flight. They might specify, well, I'm starting the flight from JFK or whatever. What are the types of actions you could take? You could take a flight, right? You could specify not only just take a flight, but I'm also taking a flight in first class, or I'm taking a flight in coach. You could also say, fair, I'm taking a flight, and it must be taking a flight in first class that costs $10,000, or whatever, right? So each one of those would be discrete actions, right? Taking a flight in first class for $100 would be a separate action from taking a flight in first class for $200. So your transition model, as I was saying, right, your updated state is where you're going to be, right? The updated state is what airport you would end up in if you took that flight in first class for $100. And the time would go in there too. So what's your goal test? Are you in the state of, is the user in the state of being in their target airport? Right? If so, then cool, you're there. Now the path cost could be defined in many different ways, right? So you could define the path cost, the transition of flight to flight to flight to flight, airport to airport to airport to airport. How much costs, a route that goes through 3 airports, if that costs $400, as opposed to a route that goes through 2 airports, which is $200. Which solution do you think you should get? You should get the one that takes you through the 2 airports, right? Waiting time could be another criteria, travel time, all type of plane. Boeing's got a lot of crappy planes flying around right now. There's not a whole lot of those I want to be on at the moment. Touring problems, traveling salesman. So in this case, the traveling salesman problem is a classic computer science problem, where you start off in a particular city and you have to end up back at the starting city, visiting a whole bunch of cities along the way, and you're trying to visit each city at most one times, right, without any duplicates. And so your goal here could be finding the shortest tour. So this is another application, the shortest trip. This could be another application of a goal driven agent. you know, that's doing these searches. All right. All right. So let's do 3.3, and yeah, I'll just tear through this, then we'll put a cut in here. I feel like I've been doing this video is dragged on long enough, and actually, in when we're under normal circumstances, chapter 3 usually takes me about 2 weeks to get through, just because there's so much here. So we'll put a cut in here after 3.3. I wanted to go through 3.4, but we'll kill it after 3.3. Okay, so as I was saying before, solutions are sequences of actions. However you define that action, 1 up, X center square, move checker from this square to that square, etc. The search algorithms are working with those sequences, okay? So these search algorithms, remember, an action is represented by an edge in the graph, right? And so you're moving from node to node to node, and you're moving along edges. And so every single time you move along an edge, that's an action. And so you keep a record of that action. And then by the time the search algorithm's done, you've got this list of actions which you return as the sequence. So that gives you a search tree, like I drew for you here a minute or two ago. And guess what? The initial state, that's the root. That was the root, right? Remember when I drew the 4 puzzle? Different branches are all the actions. Nodes in the tree, they represent, or they contain the representation of the state, okay? Of all the states in that state space. And again, how you decide to represent states within a node, it's up to you, man. As long as you are consistent, as long as you come up with something that works. I gave you some examples when I was drawing the pictures, right? So the book uses these terms, expanding the current state. So, deciding between the different actions, expanding the current state. Basically what they mean there is generating new nodes, using dynamic memory allocation to generate new nodes in your tree on the fly. So at the very beginning I talked to you about how, with traditional data structures, how you probably learned in your data structure class, you make the entire tree, or the entire data structure, and then you search on it. You're generating the tree, you're building the nodes as the search algorithm proceeds, okay? So the textbook talks about, generating a new set of states, okay? So you would start off with, dynamically allocating your root node, okay? And then you would take from that node, the state, a copy of the state from within the node, right? So inside the node, you got maybe an integer that's representing your state, or an array, or whatever. And so you grab it from the node, you grab that array, and then you feed it into your actions function. And then the actions function gives you all the actions, like we said before. And then you feed each one of those actions in turn to a results function. And then the results function gives you all your new states, and those are generated dynamically. And each one of those states is stored inside a node. One of the pieces of information in that node is who the parent node is. Okay, and so you store that as a pointer, as a reference. Okay, and so the pointers actually work backwards when you're coding this than what you're used to also. Thinking about a tree, binary search tree, B tree, it's the parent that has pointers to the children. In the way the textbook does it, does their data structures, it's the children who have a single pointer to their parent. Okay, and so why do they do this? They do it this way because you only ever have to generate as many nodes as you need to find the solution. Okay, you're not building the entire state space all at once. That's possible, and then doing your search. Okay, you're generating this search space or the state space as you're doing your search. Okay, so you would feed a particular state that's stored in a particular node to the goal test. Is this the goal? No. Okay, dynamically allocate, generate all my possible child nodes. Okay, and then in turn, examine each one of those to see if they're a goal state. If they are, it's over. Okay, it's a lot more efficient. So, deciding between different actions is called expanding the current state, and this entails generating a new set of states. Okay, so let me give you an example here, right? So the text talks about a search tree for trying to, they give you this map, in Czechoslovakia, of all places, I guess, to get from one city to another. Okay, so what you have is you have your initial state. So you're trying to find a path from Arad to, I guess, Bucharest, or let's see here, yeah, Bucharest. And so you start off, and your code would generate this first node, okay, and maybe you feed to the constructor the representation of the state, for example. Take a look at that sample code repository to see some ideas. Okay, and so you then would feed that representation into your goal test function, and it returns true or false, right? So true if the node contains the state that you're searching for, false otherwise, right? So in this case, it would return false. And so then the algorithm would continue and say, all right, let me go ahead and feed ARAD into my actions function, and it's going to generate or return to me a list of actions. So what would those actions be here? Maybe it could be travel to Sibiu, travel to Tiramisu, travel to Zebraland, whatever this is. Okay, and then you would combine ARAD with that action, and the result of that would be the Subaru state over here, which you would dynamically allocate, and then that node would have as one of its fields a pointer back to ARAD. Okay, similar thing would happen for Tiramisu over here, and another for Shaka Zulu land. And so this is called this is expanding the node by generating a set of child nodes, okay, that contain representations of the subsequent states for ARAD. Now, the algorithm would recursively continue, or it could be iterative too, but it would continue doing its thing, and then it would say, okay, well, is Subaru over here? Is this my goal state? No, because we want to get to Bucharest, right? So then guess what happens, right? You feed Subaru into your actions function. Your action function says, okay, here's some possible actions. Travel to ARAD, travel to Fogarest, travel to Orinda, travel to Rincon Valley, or whatever this is. And so then for each one of those actions, you take Subaru and you take the action, you feed it into your results function. The results function would then spit out a state that represents ARAD, and then you use that to dynamically allocate your new node, and you assign to that new node a pointer that points to the parent. And in addition, you'd also would assign to that new node the action that got you to that node, or that caused that node to be generated. If there was a cost of going from Subaru to ARAD, you'd also store that cost in the ARAD node. Okay, you'll see this more here in a second. And so this just lather, rinse, and repeats, right? Until you generate, until you dynamically allocate, until you create your goal node. Now let's say that Orinda here was the goal state, right? The goal node. Okay, the algorithm would terminate at that point. Your search is over. And so how do you create the sequence of actions? Okay, well, in this node here would be a record, or would be a field that contains the action that led to it being generated. And so you would just follow the pointers back up the tree, adding the action at each stop along the path, at each node along the path, add it to a queue, to a vector, to a linked list. And then when that's finished, when you do that reverse travel, I guess you could say, you've got a list, you've got a vector, you've got an array that has a list of all the actions. Okay, and then your search algorithm returns the answer. And so then subsequent code in your program could then use that array to update the environment. Okay. All right. So terminology for you here, you know this. A node that doesn't have children, that's a leaf node. You know that. Now the textbook refers to the set of all nodes that could be expanded. So Subaru here, all these nodes, right, that might need to have children created for them, that's part of the frontier. Okay, so search algorithms that we're going to study in the next sections, they're going to generally follow this idea. Okay, now the order in which they expand nodes, the order in which the search progresses, is going to differentiate one search algorithm from another, and also dictate how efficient one is over the other. Okay. All right. Now, if you look here, we started at ARAD, okay, and as the search progressed, we generated ARAD again, okay. So when I was doing my 3 puzzle, remember I told you there was a loop here, so we'll just ignore that. Well, you can't necessarily ignore a loop. This could become an infinite loop based off of how the actions are defined within this problem. Okay, so if that's the case, if it's possible for you to end up in a loop, then you'll have to deal with that in some way. And so the textbook is going to introduce to us a couple of different algorithms that are potential solutions for this. Okay, all right, call that a loopy path. So let's see here. So you can avoid. Here's a one possible solution to that problem. Just carefully formulate the problem, right? Write it in such a way that loops can never logically appear in the search. Okay, so that's maybe defense one. Another is to keep track of where you've been. Okay, and so you could keep an explored set, an explored list, an explored array, an explored vector that keeps track of all of the states that you have generated in the past, okay, as the search has progressed. And if you ever have the situation where that results function returns a state that you've already visited, and you'll know that because you can go check your explored set, just discard it. Don't dynamically allocate a new node. Don't create a new node with that state in it. Just ignore them. Don't make them. All right. How much further do I want to go here? I think I will go ahead and leave it here. Okay. So I'll put a cut here, and then in the next video we'll pick up and we'll look at 2 high-level pseudocode algorithms that are trying to give you a feel. These by themselves don't give you enough specifics for you to be able to translate this into code, right? There is some information that's left out on purpose. The goal here by the authors is to give you a general feel for the structure of 2 different approaches, and then you fill in the details, and those details specify exactly what type of an algorithm it's going to be. So we'll talk about at a high level the difference between a tree search and a graph search. The difference is a graph search keeps track of where it's been. The tree search up here don't. Okay, and so then we'll go through this, and maybe I'll draw you another picture or whatnot. So yeah, we'll come back and we'll resume on slide 37. So the total number of slides that we have here is 111. So probably we'll need to go through 3 pieces, right, to get through everything. That'll probably cover maybe 4, but we'll see. We'll see how it goes. I'm going to do this next video here tomorrow, and yeah. So we'll end up with 3, maybe 4 parts. Anyway, okay. Sorry for rambling. I'll catch you in the next video.